Here we have chapter 1.4, complex numbers, day 1. A complex number is a value that is involving the use of the imaginary number or value of I. And I is a representation of the square root of -1. Having the square root of -1 equal to I allows us to perform operations such as the square root of -4 to be equal to 2i. And the reason we can say that it's equal to 2i is because if we break up the square root of -4 to be the square root of 4 and the square root of -1, we can say that the square root of 4 is 2, and as we just talked about, the square root of -1 is equal to I. And so we have 2 in I to get you the 2i. If we have anytime we have a negative number under a radical, we can express an I along with however we simplify the radical. So if we have the square root of -5, for example, the square root of 5 cannot be simplified. So all we could do is take that negative part of this expression and convert that to I and then the square root of 5. If we had something like the square root of -20, then we can take the square root of 20, and knowing that that is the square root of 4 times the square root of 5 to be simplified as 2 times the square root of 5, we can take that negative part and write that with the 2 on the outside. So we get 2i times the square root of 5. So that negative is always going to be expressing the value of I, the imaginary number, and simplify the radical just as you would normally. A complex number is written in the form of a plus bi. Sometimes there are numbers that are added to the complex value, and the a part, the number that's added to the expression with an I, is the real part of the expression, and the number that goes along with the I is the imaginary part of the expression. And the A and the B values are just real numbers. I'll explain that here down below. If we have 5 minus 12i, this 5 is the real part of the expression. There is no imaginary value along with the 5, it's just 5. Now, over in the other part of the expression, we have I, and it's minus 12i. The fact that we are subtracting makes that a negative 12 for our imaginary part of the expression. If we have 8 plus the square root of 7, we need to first rewrite the square root of 7 as 7i, the square root of 7i. And once we rewrite the negative square root of -7 as the square root of 7 times I to get 8 plus the square root of 7 times I, then we know that the real part is 8 and the imaginary part is the square root of 7. So when we take that I, make sure if there's a radical value left there, the I is after the radical. Up above here, I put it as I times the square root of 5. A lot of times, you want to put the actual number in front of the I value. So like here, I wrote 2i when I took the square root of -4. I want 2i. I put the I after the number, it's like a coefficient in a variable. So in the same respect, if I have the square root of 5, that is an actual value, I'm going to put that in front of the I. And when you do that, you have to make sure that the radical only goes over the number 5 and it does not go over the I. So down here, when I did the square root of 7, I need to make sure I did stop that right before I got to the I so that it kept it separate. But regardless, our real value of the expression is 8 here, and the imaginary part is that square root of 7. All right, we're going to be adding and subtracting with the complex numbers and also multiplying. So first, we're going to cover adding and subtracting. And when we do adding and subtracting, we are performing our operations just like we would with variable expressions. So if I have I plus I, that is just simply 2I. If I have the example 5 minus 2I plus 3 minus 5I, I am going to combine like terms, and I have the real parts that have 5 plus the 3 to get 8, and I have negative 2I minus 5I to get negative 7I. And when I put these together into an expression, it is just 8 minus 7I. If I have to subtract two expressions, such as this, 8 minus 5I minus 2 minus 3I, and this is in parentheses here, I need to make sure I distribute the subtraction and rewrite this without the parentheses, and I will get 8 minus 5I minus the 2, and here I have two negatives here, or two negatives to make a positive to be plus 3I. So then I can look at my like terms. I have 8 minus 2 for my real parts to get 6, and my imaginary parts, I have negative 5I plus the 3I to get negative 2I. And when I put these together, I get 6 minus 2I. I will always put the real part first and the imaginary part second. When I get to multiplying, I must consider the fact of the value of I is the square root of negative 1. Because when I'm multiplying I times I, it's going to give me an exponent, and I will get I squared. And when you realize that you have a radical with an exponent, sometimes that exponent will get canceled out. So if I think about the fact that I have I times I being I squared, and I convert that I to be the square root of negative 1, here you will see that the exponent will cancel out the radical, and I will be left with just the value of negative 1. So therefore, I know that I squared is the same thing as negative 1. This is a huge part of complex numbers that we will need to use. I squared is negative 1. If I look at I times I times I, and I group these so that I know that I have two of them where I could say, well, I squared times I, and knowing that the value of I squared is the same thing as negative 1, and I've got this other I that's kind of extra, I have negative 1 times I, which is negative I. So I cubed is negative I. By simplifying that out, anytime I have an even number of i's, I know that they will cancel out the radical and give me a negative 1. So anytime I have two. So if I look at I times I times I times I, and I group these in pairs, I know that I have I squared times I squared, and knowing from above that I squared is negative 1, I really just have negative 1 times negative 1, and negative 1 times negative 1 is 1. So that gives me I to the fourth is 1. So I know that I equals the square root of negative 1, and there's this cycle of exponents in groups of 4 where I will cycle through these answers. the square root of -1, or I, and I squared to be -1, or -I, or 1. So these four answers are kind of going to come up. So let's look at I to the 83rd. If I have I to the 83rd, think about the fact if I had even I to the 5th, okay? When I had I to the 4th, that was 4 I's. And I know that I to the 5th can be broken up as I to the 4th times I. And I to the 4th, as we stated up here, I know is 1. So if I have 1 times I, my answer is I. So if I think about how many times I can break up the exponent into groups of 4, I can determine, every time that's an I to the 4th, that value is 1, and I'm going to break that down. So I to the 83rd is I to the 4th 20 times, because that's 4 times 20 is 80. And then there would be 3 left over. And if I remember that I to the 3rd is -I, then I can rewrite I to the 4th is the same thing as 1 to the 20th. And I to the 3rd is the same thing as having -I. Okay, 1 to the 20th exponent is still 1 times -I. 1 times -I is just -I. So I've simplified I to the 83rd by understanding how many times I to the 4th will go into 83. So 4 goes into 83 20 times. And you can do that by going 83 divided by 4. That will give you 20.75. So if I look at the whole number value, I know that I to the 4th goes into I to the 83rd. I will have 4 goes into 83 20 times with 3 left over. And I know that I to the 3rd is -I. So 1 times -I to get me -I. Okay? Now, looking at an example where I'm multiplying the expressions. So 2I times 5 plus 3I, I need to distribute the 2I. And in a sense, I'm just acting like I is a variable at the moment. So 2I times 5 would be 10I. And 2I times 3I would be 6I squared. But now because I have an exponent on the I, I need to realize that there's something special going on right there where I know that I squared is equal to -1. And so I'm going to have 10I plus 6 times -1. And 6 times -1 is -6. And if I'm adding a negative number, that's the same thing as subtracting. So 10I minus 6. But then I want to write the real number part first. And since 10I is a positive answer or positive value, I'm going to put my -6 out front, and I'm going to be adding the 10I. And that would be the correct way to write my answer, is -6 plus 10I. I'm going to do one more example here. I didn't actually set it up, but I'm going to do an example where I have two binomial expressions involving I. So if I have something like -2 plus I times 3 minus 7I, I'm going to follow the same thing I would with two binomials being multiplied, and I'm going to do the FOIL method or the box method. I'm just going to go ahead and do the FOIL method. -2 times 3 is -6. -2 times -7I would be positive 14I. I times 3 would be 3I. and I times negative 7i would be negative 7i squared. So cleaning this up, I've got like terms here with the 14i plus 3i to give me 17i positive, so adding. And the fact that I have I squared right here, and I know that I squared equals negative 1, I'm going to have this minus, and then 7 times the negative 1. So simplifying that up, I get negative 6 plus 17i minus 7 is like having negative 7 times negative 1 would be positive 7. And I'm going to combine my like terms here with the negative 7 plus the 7 to get positive 1, and I get 1 plus 17i, and that is my final answer. Okay, so it's working through just like we would having a variable, but a variable with some special properties when we run in the exponents. And that is the first day of 1.4.